My name is Serena, and I'm really excited to be speculating on an unsolved mathematical question with you all tonight. But before we begin, I want to ask a question to the audience, and I'd like a show of hands. Who has ever moved a sofa before? I know I have. Amazing. Okay, we've got some talent and experience in the audience tonight. And those of you, the majority it seems, who raised your hands, you know just how difficult it is to move a sofa. And those of you that didn't, well, you're about to find out. So without further ado, may I present to you the moving sofa problem. This problem was asked as a question by mathematician Leo Moser in 1966. So the question asks for the planar shape of maximal area that can turn around an L-shaped corridor of a width of 1 unit. And so the corridor looks something like this, and we have to move the biggest size of sofa that we can create through it. And so there are two important pieces of information that we have to keep in mind with this problem. So since this is only a two-dimensional problem, we can't lift up the sofa or maneuver it around the corner, so therefore we're only finding the area. And the second thing is, since we're only turning one way to the right, this can help us to maximize our area, the area of our sofa shape. And so one of the first models is our square-shaped sofa. And although it's relatively simple, with an area of 1 unit, it does the job. And because it's so simple, it unfortunately has earned the name the idiot sofa. But I think that's a little cruel because it serves as the baseline for future sofa models. And so arguably, it could be the most important model. But our next one is a step up from that, and this is the semicircular sofa. So to find the area of this sofa, since it has a radius of 1 unit, we can use area equals pi r squared and divide that by 2 to get our area of about pi halves, which is 1.57 units. And this sofa shape, since it looks simple, it is simple, but we can use a lot of different mathematical theorems like Thales' theorem, systems of equations, and trigonometry to explain this. But in the words of my calculus teacher, Mrs. Main, we've got bigger fish to fry, and so I won't be delving into that because the area of the semicircle by using the area of a circle works just fine. So our next model was created just 2 years after Moser proposed the moving sofa problem by mathematician John Hammersley. And Hammersley, in 1968, he took the semicircular sofa from before, he split it into 2 quarter circles, and then added in a rectangular block right in the center between those 2 pieces. And finally, he carved out a semicircular piece of about 2 over pi units, which is about 0.6 units in area, to allow rotation around our right-handed corner. And so the sofa looks something like this, and you're probably wondering, okay, what's the area of it? It is larger at an area of about 2.2074 units. And the cool thing about this sofa is it does have an upper bound as well as a lower bound area. So that lower bound is the 2.207 number, and the upper bound is a 2.8 units piece. And in a statement made by Hammersley, he said, "I had always guessed, but never been able to prove, that the lower bound was also the exact value of that maximum area." So he was never able to prove an exact area for the sofa, and he was never able to prove that 2.8 value. And so he was left with an area of 2.207 units, which makes this sofa arguably one of the best models since it was proposed. But soon after, in 1992, someone decided to one-up him. Mathematician Joseph Gerver took on the moving sofa problem, and he made a model that looks quite similar to Hammersley's, but it has a lot of differences. His model takes 18 different segments, which each have their own area, 15 of which are curved, and 3 of which, those highlighted 3, which are straight line segments. And so there, he used calculus to find his area. And so with these curved segments, the area of his new sofa came out to be 2.219 units, less than 0.02 units greater than Hammersley sofa, even though they don't look that much different from each other. But the moving sofa problem, it doesn't stop there. So a few years after the sofa problem was posed by Moser, a few mathematicians came together in a geometry conference. Mathematician John Horton Conway, Jeffrey Shepard, Maruyama, and Gibbs, and tons of other ones came together to discuss the moving sofa problem as well as a few variations. One of the variations asked for the planar shape of maximal area that will turn around both a right and left-handed corner in a hallway of width 1. And so we're not changing anything from our original sofa problem. We're just changing the hallway that it's moving through. And so in this, they created a few different models during this conference. One that's really important is E right here, that pink diagram. Mathematician Gibbs created that one. And so after waiting decades of having an unsolved ambiguous sofa problem, which is what this new subset is called, mathematician Dan Romick in 2016 from the University of California, Davis, created a new model. So he used a lot of trigonometry in this calculus because of its 18 separate arcs with 18 separate equations where he used those arcs to find the area. And so this is more of an advanced model, and it has an area, a simple equation, actually funny enough, it's not ambiguous at all, which comes out to be about 1.645 units. And so as you can see, this moving sofa moves so swiftly through our corner, and so beautifully. I love this animation. But you're probably wondering at this point, what's the point of the moving sofa problem? Why is this important to me? Why do I need to know this? And truly, there is no realistic point. As you can see, people have tried to make a realistic sofa model, and I would not want to pay $50,000 for a sofa that would give me 10 minutes of convenience. I mean, neither would you, right? So realistically, this problem doesn't work. It's only a theoretical problem posed by Moser. But the real reason why the moving sofa problem is so important to the world of mathematics is how it can apply to any level. Anyone can understand it. So if we take our square sofa from before, think back to that. It's just a shape. We're just moving shapes around a corner. That's something that a toddler can understand, what the shape of a square is. Even the semicircle, it's just a circle cut in half. A toddler could tell you that too. And a third grader could go and explain to you why the area of that square sofa is 1 unit. A middle schooler could use area equals pi r squared divided by 2 to explain to you why the area of the semicircle is 1.57 units. As we get into more advanced algebra and trigonometry, we get to Hammersley sofa at the high school level. And then when we get into more calculus-driven models, like the ambiguous moving sofa as well as Gerver's sofa, with their 18 different arcs and specific equations, then we get into higher levels, collegiate levels even. And this is where you probably think this moving sofa problem, it's still unsolved. Why would Moser create an unsolved problem? Why would mathematicians, educated mathematicians, Dan Romick from the University of California, Davis, mathematician Joseph Gerver, Gibbs, Maruyama, John Horton Conway, why would they dedicate all this time to a sofa? And truly, there is an upper bound and a lower bound to looking at this problem. You can look at it as this daunting, crazy, calculus-filled problem, or as a simple one, something a toddler can understand, like our square sofa. So most of you are probably going to be faced with the task of moving the sofa at some point in your life. And so whether you see it as that daunting task or as that simple one, that really is your choice. It's all in how you choose to look at it. So the next time that you're faced with a corner and a sofa, how are you going to figure out your own version of the moving sofa problem? What will you make it out to be? And how will you move that sofa? Thank you.